All right, thank you all. All right, now we can go ahead and get started. So, as he said, the title of my talk is Real-Time Unsupervised Clustering. And let me first begin by talking about what kinds of work I do that motivates my interest in this problem in particular. So, I'm a roboticist. I like to build robots, program them, hook cameras up to them, and see what I can make them do. One of the really interesting problems that arises in robotics is that of modeling the robot's environment. In particular, you can imagine that any interesting robot is going to be configured with multiple sensors that have continuous valued inputs of some kind. If you imagine range sensors, for example, those sensors are giving values that are distances in meters, which includes fractions and the like. If you imagine the use of cameras and images, you've got some m by n matrix of color and intensity values. Now, if you want to think about the problem of action selection, you don't necessarily want to come up with a separate action for every imaginable sensor configuration. Rather, if you can create a compact, discrete model of the robot's environment, that creates the possibility of working out some appropriate action mappings for different sensor inputs. So I've been doing a lot of work in this area, combining the self-organizing map with Q-learning. There's some prior work using dual self-organizing maps. I've also made use of growing neural gas. And the general theme is if you can cluster the sensor values into a small number of clusters, from there you can specify the appropriate action to take if a new sensor input comes in that corresponds to the given cluster. So this, however, requires performing the machine learning task in real time. That is to say, as the robot drives around, what I'm seeking to do is to have it build its model of the environment in an online way. As the robot drives, the environment gets built up. Ideally, what we want to do here is to enable the learning algorithm to incorporate new examples into its data structure within the cycle time for the robot to process its sensory inputs and select an action. So that's what leads to my characterization of this as a real-time machine learning problem. One iteration of training, that is the incorporation of one training example into what it's learning, should take constant time. In fact, why constant time? If it takes constant time, we can make guarantees about the amount of wall clock time necessary to complete a cycle of sensing and action. Now, something that's very important here is this cannot depend on the prior number of training samples. No matter how much it's seen, it still needs to fit that constant. Constant time might seem like a strong term, and so I want to emphasize here that if we're talking about training n samples, we're really talking about linear time. However, what I want to be clear about is that after each sample, the algorithm must be updated and ready to go. If we're going to train n samples, we need to have met n deadlines in order to satisfy the criteria of interest here. In particular, we want no amortized time. So we don't want to be in a situation where we might amortize an algorithm such that on each cycle it amortizes to constant time, but every now and then it sort of has to stop the robot and let it do an O of n computation before it continues. That I am explicitly rejecting as a permissible solution for the kinds of situations that interest me. So one clustering algorithm that has been used in the past both by myself and others that meets these criteria is the self-organizing map, the Cohonen self-organizing map. Brief overview of this algorithm. A self-organizing map is a type of neural network that's trying to model how the neocortex forms abstractions. So if you think about the idea of, say, a cup, just to think of an example that happened to be right in front of me. In my neocortex, I have formed an abstraction of the idea of a cup, which in turn I can employ when I'm sensing to try to impose some semantics on my environment. This representation is ultimately derived by doing some kind of incremental averaging of new sensory examples that come in to my visual system, and from there into the neocortex. And the self-organizing map aims to emulate aspects of this cognitive process. So to this end, it consists of a two-dimensional grid of reference inputs, or clusters, so ideal inputs that are representative of the cluster. To train on a given input, we first figure out which element of the grid has the lowest sum of squared difference with the input. So this implies that you've got some kind of distance metric. For all of the examples I'll be using, it's a Euclidean distance metric, is what I've been employing. And from there, once you find the winner, there's this update function where the idea is moderated by a learning rate, an alpha term. You calculate the difference between each element of the input vector and the vector of the winning reference input, find the difference, multiply that by the learning rate, and then add that back into the weight vector for the reference input. That in turn allows us to do incremental updates of the winner in an online way. So the algorithm never stops learning. It's lifelong learning, you might call it. To think of a buzzword that appears from time to time in academia. So the question is, well, what do you use for the learning rate? For a real-time formulation of the self-organizing map, you have to be very careful about this. The learning rates that Touzet used in some work he did with the self-organizing map, for the winning node, you use 0.9. So that implies that there's a nearly equal balance between the values of the input and the values of the reference cluster that's already there. And for the four cardinal neighbors of the winner, a 0.5. And so this forms kind of a continuous surface. And we'll see an example of that in a few moments. Now, a more classic formulation of the SOM is not as an online real-time learning algorithm. Instead, the more traditional formulation is to make multiple passes over the entire input set, starting with a high learning rate and a very large neighborhood of affected nodes. After each pass, they get slowly decreased in order to form a really nice continuous looking surface. That said, the advantage of this Touzet SOM is that we have a real-time formulation of clustering according to the criteria I set out earlier. That is, we can say each input is processed in a constant bounded amount of time. Keeping it simple, what we observe is that given an n by n SOM, at most we are doing n squared distance comparisons. But because n is a constant, we can argue that each one is being done in constant time. Thinking about this in terms of a robotic engineering problem, what one can do is determine an n that allows the robot to complete its cycle time with whatever your desired result is. You know, given whatever hardware you have and so forth, you might say each cycle needs to complete in 1/5 of a second. You set n accordingly and it'll work. Of course, the bigger the n you have, the better a model you might have, and that's just part of the trade-off of the particular hardware you have available. So, a key property of the self-organizing map, a key design idea, is to maintain coherence of the neighborhood. So here I have a 7x7 self-organizing map that I trained on some handwriting samples. These handwriting samples came from someone with amazing handwriting, namely me. So not so amazing, of course. In all seriousness, if you look at this, you see that it does a really neat job of forming neighborhoods of similar inputs. If you look over here, you've got like the S zone. This is the S part of the map, but S gradually turns into the rather similar B as you migrate over here. And this is because of the way the training affects not just the winning node, but the neighbors. If you come down here, S gradually becomes A, and A in turn becomes M, which in turn becomes V. So we have transitions between different types of inputs and reference values for those clusters that correspond to them accordingly. That said, for the kinds of tasks I'm interested in, this neighborhood coherence I was observing just as I was getting frustrated with some experiments was actually turning into a bit of a deficiency for what I was trying to achieve. That is to say, because it preserves fine gradations between clusters, this works great if you've got lots of time and space. You build a nice huge grid that's got lots of reference inputs for every cluster, it works beautifully. On a robot, you typically have neither. And so I was trying to replicate some of the prior work, and I found that the clusters didn't represent my sensor data very well. In particular, that led me to try to formulate what is it that I want in order to have a good environment cluster. And this is the metric that I decided upon. The sum of squared differences between each input and the best matching cluster is my metric. For the performance across an entire data set, what I do is, after training the data structure, calculate the sum of squared differences across all the inputs. I always use the same number of inputs for every experiment, so you might just think of this as a poor man's average. But that's essentially what I'm trying to achieve here. The goal, loosely speaking, is that I want every sensor input to be reasonably close to some cluster. And I was finding in my use of the self-organizing map I wasn't really achieving that in a satisfactory way. So, formulating this metric led to the formulation of a new clustering algorithm to try to improve performance relative to that metric, which I'm calling bounded self-organizing clusters, designed to outperform the SOM on our metric. Key insight behind this is, in principle, given this metric, if you really want to maximize performance, what you want to do is simply retain all inputs. If you do that, and then every single input, of course, has a perfect match among the clusters, and the metric is good. Of course, that's not going to be a real-time clustering algorithm because the number of inputs is continually growing. So we need a constant bound on the number of clusters. Given that, the solution that I'm investigating in this work is to retain all inputs until a limit is reached. And once that limit is reached, begin merging similar inputs. So, the underlying data structure is a complete undirected weighted graph. Each node is the reference input for a cluster. The edges are the Euclidean distances between the matching reference inputs. Because every pair of nodes has some defined distance between them, that is why we have a complete graph for this purpose. The edges then are stored in a red-black tree so that you can quickly find a smallest edge for the merging process. So here's a brief pseudocode for the algorithm. To set it up, just initialize the edges with a red-black tree. The nodes are simply a fixed size array. To do a lookup, you just check the distance for every input between the input and every node, and then return the index and distance of your closest match. To train, you first go ahead and insert the input into the array. Now, if this causes us to exceed our maximum number of nodes, we remove the edge which is smallest. Whichever the smallest edge is, we take that out. The endpoints of the edge, we remove both of those nodes and then all of their corresponding edges as well. We merge the nodes and insert it back into the graph. To insert, we just add the image. We add the image we're inserting to the nodes. Then for each existing node, we find the appropriate edge size, insert the corresponding edge. So we have to do that for every existing node. Merging is a simple average for this first iteration of the algorithm. We just average all of the corresponding values in whatever the input vector is. So in terms of the time complexity, if we let m be the maximum number of nodes that we are willing to permit, lookup and insert just do m calls to the distance function. Insert also does m squared edge insertions with a red-black tree. That's 2m log m comparisons. Training does 2 calls to insert in addition to 2m edge removals, 2m log n comparisons again. Since all of these operations are in terms of m, which is a constant, we can say the update happens in constant time. So I implemented that first version of the algorithm, and I'll be showing some data on it in just a couple of minutes. But I first want to make some observations that I wasn't thrilled with some of the data I got with the first iteration of it. And my intuition was that it was not making a distinction between clusters which were raw input samples and clusters that were the result of several iterations of merging. My intuition was these are fundamentally different kinds of things because clusters which are the result of multiple merges should be closer to a larger part of the overall input space than these clusters which are just the raw input samples. So I came up with an alternate version where each node maintains a count of the number of source inputs. This count then is used as a weight in two different ways. First of all, it enables us to do weighted averages when merging. So if you've got a node that has a lot of inputs feeding in as a source, what you want to do is when you compute the average, allow that node to be dominant in the average. The new input coming in can move it a little bit, but you don't want it moving it halfway, you know. Then we also wound up using it as an edge weight multiplier. So the idea is a node that's the product of a lot of mergings, we want to try to keep that relatively stable and encourage nodes that are the product of simply one or a couple of inputs to merge. So that if we look at the overall space, we have lots of merged nodes and not a whole lot of singletons. So this does require changing the algorithm a little bit by adding this idea of a count. So now when we train, we insert initially with a count of 1. When we do a merge, we insert the merged result, and then we also add the counts together. Okay? Then when we do the insert, when we insert the edge, we multiply by the larger of the two counts. The larger of the two counts. When we are merging, we perform a weighted average, as outlined here. So we sum the counts and then use the numerators to help perform a weighting. So I did a series of experiments with the self-organizing map, the first non-weighted version of the BSOC, and the second weighted version of the BSOC. For my data sets, I collected 3 data sets from one of my robots. One was a sonar data set with a 3 sonar array in front of the robot, and then also 2 video data sets, which I'm going to share with you now. These are a bit sped up for conference presentation purposes. This is in my office. I want to just give you a feel for the carpet, what kinds of objects there were, and so forth. So it's sort of a gray carpet. Let me give you a feel for the lighting conditions. There was some both natural and artificial light present in this environment, as well as obviously shadows and other such things. So there we are. The other video, I wanted a different floor surface and slightly different lighting conditions. So in the second video, this is a lab in our department that had a tile floor and no natural light, strictly artificial light. There we go. Okay. Whoa. Let's try that again. There we go. So zipping around this computer lab, running into boxes. There you can see the tile floor a bit, black and white alternating, so forth. Little view of the hallway, my shoe, whoops, and so forth. So just wanted to get a feel for how it did under some different conditions. So this preliminary table of results, for all 3 algorithms, I experimented with 16, 32, and 64 as the maximum number of nodes. What I'm presenting here at the top is for my sonar data set. This is in terms of meters squared because we're talking about sum of squared differences. Here the difference between BSOC and the SOM was fairly drastic, about 2 orders of magnitude improvement with the new clustering algorithm. The improvement wasn't quite as drastic with the video, but was still substantial. As I looked at these figures, I thought, with all these crazy exponents, it was a little hard to read. So what I did was I redid the data in the following form. This is the same data, just presented differently. I put the sum of squared differences in the numerator, and that for each of the BSOC variations in the denominator, so that we could see a multiplier of how many times greater the sum was for the SOM as opposed to the BSOC implementations. So for the sonar, we can see that, for 16 nodes here, for instance, it was 78 times greater than for the BSOC. When we get down to the videos, for the unweighted formulation of the BSOC, for the first video, it was 1 to 2.5 times larger. For the second video, it was a bit more, 3 to 4 times really. For the weighted version of BSOC, there was a much more significant improvement. So 16, 32, 64 were 3 to 4 times more. Then with the second video, we're looking at 11 times, 8 times, 16 times more. So some pretty, this is anecdotal, obviously. This is very much a work in progress, but the improvements were still pretty compelling, I think. So for my next steps, I'm still continuing to experiment with using this for environment modeling. That said, another direction I'm looking at is to actually use this as a subcomponent for a supervised learning algorithm. The idea would be to use this clustering approach to create a variation of k nearest neighbor. Now, k nearest neighbor by itself is not a real-time learning algorithm because k nearest neighbor retains absolutely all of its inputs. I think it'll be really interesting to use BSOC as a subroutine for k nearest neighbor and try to do some measurements of what you might call the real-time penalty. What penalty do you pay for doing this compression of the inputs into these clusters in exchange for having these guarantees? And so that's a study I'm going to be working on over this coming summer. By formulating this as a supervised learning problem, this also gives us the opportunity to try to assess this algorithm against a better known set of benchmarks. Unsupervised learners don't really have the kinds of well-established benchmarks that supervised learners do. And so this is going to give us a chance to better characterize the overall performance, I think. Another thing we're going to be looking at is using pre-processed image features. Right now, for the images, we're just doing sum of square differences over the pixel intensity values, which, while effective as far as it goes, is really not ideal. We're going to be looking at using some pre-processed features. So to wrap up, we're definitely able to outperform the SOM on the SSD metric. Our weighted version outperforms the basic version. It's what we would recommend if you want to try this. I really think it's got some great potential. I've got my complete implementation and data sets available on GitHub if you want to mess around with it. If you do, let me know. There's my email. Thank you very much. Yes?
Okay, so how is real-time learning different from one-shot learning, other than that this is unsupervised and that is supervised?
Could you give me a quick definition of what you mean by one-shot learning?
Learning by one or very few examples.
Okay, that's a great question. I'm not as concerned here with, for example, making sure that it learns something really good with a small number of examples. I'm content to say, drive my robot around for 10 minutes, building its model as it goes and having a model that's induced by a larger number of data samples. Good. Other questions? Yes?
This might be related to your idea of using it for a k nearest neighbors approach. But in your experience with this algorithm so far, would you say it has potential to be used as also a math refinement? Because I've actually been, and I can give you an example of what I mean. I have a lab with I work with some undergrad students at IPFW, and recently they tried to have some vision processing to get a Roomba down to a coffee shop in our building, and we ran into issues with both an OpenCV approach and a neural network approach. And so I see this, and I'm wondering, could we use this to self-correct?
Yeah. I am heavily interested in that. Okay. We should probably talk offline afterward. But what I would briefly say is, yeah, I think this has got huge potential in that area, but it's a very open research question. Okay. I'm just starting to look at it.
Any other questions? Actually, I have a question.
Sure.
I remember last you mentioned about image features.
Yeah.
Actually, I did a project for indoor environment localization.
Uh-huh.
What we do is actually use a robot to scan the environment and then try to reconstruct a 3D space.
Right.
And then it will be used for image localization. When people send an image, they can find where
right.
they are.
Mm-hmm.
But the big problem is that there are a lot of repeated patterns. Like
right.
inside the environment, there are walls. So I'm thinking like maybe we can cast that problem into like a clustering problem. So after this kind of environment, based on the features, we can cluster. This is maybe a wall area.
Yep.
This is office. Will that be doable for you?
That's a big part of my vision of where I think this could go. Okay. What I've been looking at is trying to use brief features because they're really fast to compute. You know, there are these binary intensity features, and so that's something I was planning to work on this summer. And again, we might chat more about that offline as well.
Great. Other questions? Okay, now let's thank the speaker again.